excellent. So let's get started. Let me tell you a little bit. First of all, let me tell you a little bit about the agenda for today. So the plan is to talk briefly about Android stack. We're just gonna kind of cover the basics. It seems like most of you are familiar with that already. Then we're gonna talk about security essentials. As part of that, we're gonna talk about the architecture. So basically, how is Android architected in terms of the security. We're going to talk about application signing. We're going to talk about UIDs, how they work. We're going to discuss file access, multiple user support that was added in 4.2, and we're going to talk about permissions. And as part of that, we're going to do a little lab on adding permissions to an existing application, so you kind of have first-hand knowledge of how that works. Afterwards, we're going to talk about the advanced security. So as part of that, we're going to talk about the encryption, both basically application level encryption as well as the whole disk encryption. We're going to talk about rooting and issues that come with that. Then we're going to talk about device administration, malware. We're going to mention SE Linux, and we're going to discuss some other concerns. So that's basically the plan for today. I believe we have just under 2 hours, if I'm correct, and we may or may not do a break. Depending on how we go. So just really briefly about myself. So my name is Marco Garganta. My background is in Java. I've been doing Java since before it was Java. And I've been doing a lot of Android from the get-go, so from early days on Android, when Android came out. And in the beginning, I was mostly focused on app development. And I developed a course called Android Bootcamp. As part of that course, I basically traveled all over the world training developers on how to build apps. And that was a couple of years ago. I bottled that course into a book called Learning Android that's been published in Chinese, English, German, a couple other languages. And it was one of the top 10 bestsellers. I haven't checked lately. So lately, what I've been doing is mostly focused on Android internal. So basically, what happens under the hood? How do things really work inside of Android? So that's been most of my recent sort of focus. I frequently speak at conferences. This is my, I believe, third time. This is the third conference, third Android Builder Summit, so third time here. And I frequently speak at OSCON and DevCon and similar. So that's a little bit about me. So you guys are probably already familiar with this stack. You've seen a picture like this before. Let me just resize this so we can fit on this small screen. So basically, as you guys know, Android is based on Linux kernel. On top of that, we have the native layer. In my pictures, green roughly represents C, C++, blue roughly represents Java, but it's not always like that. The boundaries are not nice and perfect like we have on the picture. So basically, above the native layer, we have the application framework, and then finally we have the apps. So each layer has its own security concerns. So we're going to cover those as we keep on going. So the basic premise of the architecture in Android is that basically apps cannot talk to one another. So basically each app is isolated, and this isolation happens by the kernel. So essentially, what I have in this picture is a set of applications. We draw them as these vertical boxes. So basically, each vertical box represents a process. And if you kind of consider this over time, so if this is a boot time, so this would be time 0. So basically, processes get created this way. So initially, we have the kernel that starts. So kernel, as part of that, launches a few daemons that are needed. So involve D, net D, install D, etc. So those are basically your native C, C++ services or daemons. After that, we have the service manager. That's basically the naming discovery service for all the other system services. That starts next. After that, we have Zygote, which is the mother of all Android apps. It's basically the initial app that gets spawned whenever you want to start any other Android application. So that gets started. That initializes Dalvik, initializes all the libraries that need to be loaded into Dalvik, and so on. And finally, we have system server that starts, which basically boots up all of those 60, 70 different services, so everything from location to Wi-Fi to Bluetooth to networking to audio to vibrator, NFC, etc., etc. So all the services basically get started under this umbrella of the system server, which is basically controlling the access to them. Once we have all that started at about this line in the timeline, we say the boot is completed. So that's basically when the broadcast boot completed gets sent out. After that, the apps start. So basically, we have the home screen. Technically, home screen starts before that line, but it's not on the picture. But basically, we have Android applications start after that. The point that we wanted to kind of clear with this picture is that the apps cannot talk to anybody else, right? So basically, an application like App 1 is not allowed to talk to another app, is not allowed to talk to a system server, is not allowed to talk to Zygote, a service manager, nor any of the daemons or kernel directly. So how does that work then? So Android is basically a privilege-based operating system, which basically means that each app runs in its own process, and if an app wants to do something, it needs to have the permission to do that. The permission to do anything in Android is ultimately handled by the kernel itself. So the kernel basically checks who can do what. So in other words, kernel does this isolation between various processes. So by default, an app is not allowed to do anything that can adversely affect the user, other apps, or the system itself. So in other words, if it's about reading personal data, that affects the user. It's a privacy issue. If it's reading, for example, accessing internet, it can cost user money. So that's a cost money issue. And if it's, for example, keeping the device alive, awake, keeping the screen on, for instance, that's adversely affecting other applications because it's wasting the battery. So any of those potentially dangerous things, an app is by default not allowed to do. We're going to discuss how permissions work later on and how that's actually implemented down at the low level. So basically, we have the fine-grained permission system in Android. The permissions can be enforced statically, or they can be enforced dynamically. They can also be granted dynamically at runtime in certain cases. So we'll talk about that. Apps can talk to one another via certain systems. Binder IPC is one of them. Intents is a specialized version of Binder IPC mechanism. So that's another way to communicate, as well as the content providers. They also offer another binder-based mechanism to exchange the data, the content between applications. But again, the rights to access that are enforced by the kernel. So the Linux kernel is ultimately the sole mechanism for ensuring this. And this is sort of something that's very interesting about Android and Android security design that's very unlike other Java-based operating systems like BlackBerry, for example. So kernel is the ultimate enforcer of the security. So we say that all the applications are created equal. There's going to be a slight difference between those applications that are actually installed on the system partition versus those that are installed on the user partition. But other than that, the code itself is the same. So they can just have a different level of security depending on where they're installed. So we'll discuss that in a bit. So I mentioned application sandboxing as a concept. So basically, what we have is we have something like this when it comes to an application. So each app in Android is a Linux process, right? And each app is going to have its own instance of Dalvik. On top of that, each app is going to have any number of activities, services, providers, or receivers, right? Those are the basic building blocks of Android. Within that application sandbox, we're also going to have various data. So we're going to have possibly databases, files, resources, permissions, native libraries, etc., etc. So that's basically all contained within a single process. So that's the premise of the sandboxing mechanism that Android has. Applications are signed. So an application, before it can actually be shipped to a device, is packaged into a so-called APK file, which stands for application package, and it must be signed So basically, the point of the signatures is really just to clarify who the owner is. In other words, the owner of the application can prove that he or she is the owner of the application, but it doesn't certify the identity of the owner. So there's no provenance basically around the actual identity of the creator of the app. We just know that an application belongs to somebody who owns the signature. So it basically, it's usually used to create a trust relationship between applications. So applications with the same signature can establish a trusted relationship among themselves. The signing process is using a very standard public key cryptography, the same technology that Java uses. So in other words, we just use the Java key tool. It's a standard key tool that all of you have as part of your JDK. And we basically sign applications. By default, all of you guys actually have a key that's located in a directory that you have under your home directory. So on my system, that would be basically cd.android. And in this directory, there's basically a debug key store. So that's the key store that Eclipse is going to create for all of you, and that's what we're using in the development process. If you actually wanted to create your own key store, you can do that multiple ways. You can use the key tool, which, as I mentioned, is the standard key tool, and you can generate a key that way. Or you can use Eclipse, which has a built-in preferences Android built default key store system, so you can basically create the key tool that way. There is no, when it comes to this key tool, one thing that I already mentioned, there is no certified authority in the world of Android. So this is also one place where Android sort of departs from other ecosystems, right? All the other mobile ecosystems have sort of the certified authority, somebody you go to actually verify the ownership of an app. In Android world, you create a key, you say who you are, and nobody really checks any of that. Google has a specific policy, but this is now just Google in terms of the Google Play Store. And they ask you to have a key that's valid for at least 25 years, that you use the same key to encrypt all the applications that come from the same organization or the user, and so on. But that's just specific to a key store. So basically, you can verify a key. For example, you can use the key tool just to kind of check the authenticity of a key. So if I try to run this against my debug key store and I leave password blank, I'm going to find out a little bit about who this key belongs to. So it's going to tell you that this is just my debug key. So there's not really much in it. But if you created your own key, you would basically be able to verify the ownership that way. There's also a jar signer. This is an alternative to using the standard key tool. Jar signer just uses a jar that you can download, and it basically command line looks like that. It's pretty straightforward, and you can use it to basically sign your applications that way. Once an application is signed, what basically happens, it's zipped up into a zip file, which is essentially what APK is. And as part of that, we have the manifest file, which now describes the signatures for every single app. So in other words, the files themselves are not modified. What happens is there's just basically an entry, the manifest file, which specifies the signature or the digest of a specific key to kind of identify its size and content at that point in time. So this information is stored in a meta-inf folder. Just to give you an example, I created Android Builder Summit. I built a couple of apps here that I'm going to be showing you later on. So if I just pick a random app, secure node, and actually I haven't run it, so let me just run it so that it actually gets installed. So if I run it, and if I go into the bin folder, the Eclipse is automatically going to create secure node.apk file. Like I said, this is just a zip file. So if I was gonna make a temporary directory and just unzip it, we basically see, let me just show you like this. We can see that the content of that secure node APK file is really just the classes themselves, so the Dalvik code that's zipped up, the resources, right? The manifest file, which we're going to talk about later, which specifies all the components that this application is going to use and permissions that it requires. And in addition to that, the only new thing is the meta-inf. So that's the directory that basically contains the signatures for each specific file that's part of this application. So those are the certs and the manifest. So all this happened behind the scenes by Eclipse since we're in the development mode. So, so that's a little bit about the as part of the final compression of the files, there's also something called zip align, which basically just ensures that the files are nicely optimized in terms of the memory allocation, so that it can run faster when it's actually installed on a device itself. So, so that's a little bit about the signage of applications. Now, most of you probably that built Android ROM probably know of this, but as part of the build process, the platform itself also has keys. And as a matter of fact, it doesn't have one key, but it has 4 different keys. And this is a pretty common mistake or something that people overlook when they build ROM. They basically don't replace those keys because AOSP doesn't force you to do it. You already have the keys that are installed. So just to kind of show you that, what I'm going to do is I'm going to mount my, I believe I have it actually already mounted. So let me actually make sure that I have the right AOSP. So I'm going to mount this one. Source and so if I go to this directory, these are the keys that ship with AOSP as you get them. So often people don't remove them. So they're based on the same principle. So it's the same key tool. None of it is different. The only difference is that you actually need to generate 4 different keys, and they're used for 4 different things. So basically, platform is used for core frameworks. So it's going to sign about half of the core frameworks. Shared is used for the applications, especially the applications that are shared by the systems, like content providers and such. So that's a shared key. Then we have a media key, which is used by DRM, by gallery, a couple of applications like that. And finally, the test key, which is used by everyone else on the platform. So the proper instructions would be to blow away those keys on the ROM in the source tree itself, to create the signer, to basically specify who the signer is going to be, and to basically then run the platform make key tool, which basically ships with AOSP, but ultimately does the same thing as key tool, and generate the 4 keys for each platform. So this is how we would basically generate the platform key, and I would repeat the same step for media, shared, and test keys. Yeah. Basically, when it comes to management of the source code, I usually recommend keeping your changes to the source code outside of the main tree, right? So basically keeping it in /vendor or something like that. But when it comes to keys, because there's no real good reason why would they even have the default keys, and they can just lead to mistakes in the build. Right. I mean, exactly. I mean, you can do it that way. The only problem is if you actually make a mistake and don't point to the right keys, then it's going to not tell you that it's using the platform keys, and it's going to find them and it's successfully going to use just the standard platform keys. And that leads to problems later on, because if you end up actually distributing a ROM that you actually signed with the default keys, anyone can provide the update.zip for that ROM and can basically do anything they want to it. So that's why, if you know what you're doing, you can have a separate copy, or you can just blow them away and not even, cool. So that's a little bit about the platform keys. So let's talk a little bit about user IDs. So basically, Android has users, but it doesn't use the users or UIDs the same way Linux does. Essentially, they are only logical users. They're not physical users. In other words, you cannot have a user Bob, right? So what happens with Android UIDs is they represent the actual application UIDs. Up until Ice Cream Sandwich, they were of the format app_xx, where the xx was basically a number that was assigned to each application at install time. So install D does that. And they actually map into the UIDs that start at 10,000. So that's essentially what that looks like. Let me just kind of do the following. I'm just going to do the ADB shell and run a PS on my emulator. So these are the users that I'm talking about. So essentially, the very first process that we have, the init process, has UID1. And after that, we basically don't have anything super interesting up until Zygote starts, which now, in this case, is the 795. So this is basically the first Android app, or the mother of all Android applications. What's going to happen next is every single Android application that ever starts is going to have that as the parent process. And the so-called underprivileged Android apps, so the regular Android apps, they're going to have the user ID that's off format, such as U0_A and then something something. Now, this is a new format. This format was introduced in Ice Cream Sandwich under the hood, but it was really introduced in Jelly Bean, or exposed in Jelly Bean to the users as part of the multi-user support. So we'll talk about that in a bit. But basically, these users now represent the actual app UIDs, and that's how kernel now enforces the security. So so when I install a random application, like for example in this case I just have the secure note application that I just ran, it's got a user of U0_A59. So basically A59 maps to the old app59 user ID. So basically these mappings represent. We can actually see these mappings if we just cat the system package list. So for example, if I'm looking for a specific application, I can see what that application UID is. So for example, if I want to know what browser is running as, okay, so the standard Android browser in this case is running under the UID of 10,014. And that actually maps to U0_A14. So that's going to be the UID. So which, if I do ADB shell PS, you can probably see somewhere here if it's actually running at all. And we don't currently have it, but if I just start the browser, that should be easy enough to start. Except that this emulator is not going to work this way because of the screen resize when I connect it. So let me just restart it. So we'll see that in a little bit. So again, that's how the mappings happen between the users and the actual apps. At install time, what happens is when you download an application, that application gets stored in a quarantine space. It goes into a temporary folder. And that point gets analyzed by install daemon. And so basically, it looks up at the application, analyzes its manifest file, and at that time, once the user actually grants the permissions, which we'll talk about later on, to that application, install D is the one that actually assigns it the UID at that time and installs it. So we'll see that in a bit. So do I have this started? I do. So if I just launch, for example, browser, we should be able to see that the browser is indeed running under A14 user. So that's the browser right there. Again, this is not going to change for the life of this application on this device. The file that manages all this is in the data system package list. So if I cat that on this device, you can notice that every single application that was ever installed is basically given the package name. So this is going to be the unique ID of that, the unique name of that application on this device. So that's how the application is signed. That's how it's known. This is going to be its UID, which, as we said, maps to on a multi-user, on post ice cream sandwich devices. This maps to U0 and then A48. And what we have here is we basically have what this application is using as its private data storage. So we'll talk about that when we talk about the file system access rights. So that's briefly how that gets installed and how the system keeps track of that. So the users in Android are quite different than the users in Linux, but underneath they're leveraging the Linux UIDs, and that's how the kernel is actually enforcing the security ultimately. So we basically saw those things. It is possible to have multiple applications run under the same user. And this is often done when you sort of have like a federation of applications. So, for example, if you're developing extensions to the framework, or you just have a system where you actually have multiple apps and those applications need to communicate, what you can do is you can have them run and share the same UID. When they share the same UID, they ultimately are considered basically a same application, having the same access rights to the file system, permissions, that sort of thing. But for them to actually be able to share UIDs, they must be signed with the same key. So this is only possible when they're signed with the same key. So that's what the key enforcement again comes in handy. So ultimately, what we're doing in this case is we're defining that application runs as a specific process. So if you don't specify that, application is just going to run on its pre-assigned process. So that's this is the manifest file. And we're using the shared user ID. We're using the shared user ID property of manifest. So we briefly touched the file system. So just really briefly, let me kind of give you a quick overview of the file system on a typical device. So from a security standpoint, so basically on a typical Android device, we have a file system. There are a couple of partitions that are kind of interesting to us. System partition is one of them. This is the operating system itself. So that's essentially the ROM. This is the partition that's about 200-300 megs when it's all said and done. What's important about this partition is that it's mounted read-only. So basically, an app developer or a user, in theory, doesn't have any access to this partition. So I'm assuming a non-rooted device, because if it's rooted, all hell goes loose, basically. None of this matters. But the non-rooted device, there's basically no access to user or apps to this partition. What that ultimately means is that this partition doesn't contain any user data. So in other words, from security standpoint, we don't really care too much about backing it up or encrypting user data on it, because there shouldn't be any user data to begin with, right? So that's basically the system partition. The other one that's very much of interest to us is the data partition. This is the user data mount point. So basically, this is a read-write partition. What we have on it is we basically have all the downloaded apps, and we have the data, not just for the downloaded apps, but for all the apps in general. So basically, all the applications are going to store their data there. So the user downloaded apps are going to go into data app folder. So each application is going to be in here. So these are the APK files that came from the internet. You may notice some ODEX files. Those are the optimized DEX files, which basically got extracted from often extracted from the APK file, optimized for a given platform, and then stored as such as ODEX files. So these are the user downloaded applications that we can uninstall, that we can upgrade, etc. The data for all the applications lives in the data folder. So from app developer or user standpoint, this is the most important place, because each application is gonna keep its data in this folder, and this is true for both system and user downloaded applications. So if I, for example, take a look at a random application, so I'm going to cd into data data, and I'm gonna cd2 Maracana. Let's see, Maracana, Android, Yamba, for example. I have an application. What's interesting, so I'm in this folder. What's interesting about this folder is that it is it's basically owned by the that user. So we have the U0A54. So that's the app that was assigned, the user ID that was assigned to this application. So both user and group on this directory are belong to that particular application. So AL. So as you can see, for all the applications, this is the case. So we have basically a sandbox on the file system. They're unreadable to anyone else other than the user and group, and the user and group belong to that particular application. So this is how the sandboxing of the actual file system is managed on per application basis. So that's a little bit about the file system in general. We also have the, other than user and system partition, we also have the SD card partition, which in this case is the mount SD card. And SD card partition used to be free for all storage, so you actually didn't even require permissions to read nor write to it up until, I want to say 1.5. Then they introduced the write permissions. So basically, now it's potentially dangerous to write to it. So you can read from it, but if you want to write, you need to ask the user for access to that. So as such, it's not really all that managed by the system. They're getting a little better about it. We'll talk about the OBB section later on. But that's the SD card. SD card is managed by the volume daemon. So we'll talk about that in a bit as well. So that's the partitions that we talked about. So there's also a /cache, which is used for transient data, browser cache, etc. So these are the partitions that we just discussed. You can use the PM package manager to find out the specific partition location of the sandbox for a particular application. So for example, if I do PM path, I can ask based on a package, so I can find out where a specific app is installed or what file this application is installed under, because it doesn't have to be installed under a nice looking file name like this. It could be a totally arbitrary file. So for example, if I did Maracana, Android, Yamba, so we now see that this file name is actually a totally different file name, so it's -1. Or something. So there's no significance. In other words, there's not a lot of significance in the file name itself, whereas the package name is important. Under each sandboxed application, so under each application, we basically have a lib directory as well. So this directory is used to place possible shared libraries, so SOs, the native libraries that you could ship with your application. So if you look at that on the /data partition, so if I go /data and I pick some random application like gallery, for example, you'll notice that there's a lib directory. Now, for almost all, as a matter of fact, all system apps, this directory is always going to be empty. And for majority of the built-in downloaded applications, it's also going to be empty. It's only for the applications that actually contain some native libraries that there may be something in it. So let me show you an example of that we have. So let me just make this a little bigger so you can actually see. So I have something called native. So this application contains a library. So this is a native library that's placed there. So in other words, there's a lib folder that's part of the LD library path for each individual application, and in most cases doesn't contain anything. We'll talk about this when we talk about multi-user support since Ice Cream Sandwich. But basically, this location has actually been moved and symbolically linked to. So for multiple users, we're actually going to have a different location for different libraries as well. So basically, that's a little bit about the file system, how it's organized, and how the permissions are enforced on it. what's also interesting that we didn't talk about at the startup time, the init process goes through all the mount points and actually sets the permissions. So unlike a traditional Linux operating system where this would be something that's statically managed in fstab or some file like that, on Android, init resets the permissions on the files every single time. So so if we do mount here, you can actually see what the mount partitions we have. So I was talking about the SD system partition, so that's where it's mounted read-only, right? And we were also discussing the data partition, which is somewhere here. Next one down, yeah. So this one is mounted read-write, yeah. But what I wanted to show you, which is going to be easier to show you here, is go there, init.rc file, and let me go for 4. So let me try to fit this on the screen. So this is the init file that is run by init process as the very first thing that kernel does. And what happens is it actually creates all the folders and sets the permissions. So you can basically see how init is every single time at every single boot setting up what the access rights are to /data to 771 ownership system, right? It's mounting various directories. So in this case, it's mounting the mount secure and so on and so on. So basically, every single time we are configuring the access to various partitions. This is where this is the point where the system partition actually gets remounted read-only. So it's not like that the ROM itself is not physically writable. It is. It's just that init makes sure that at mount time it actually marks it read-only. So that's what makes it unaccessible to anyone but root, for example, who could remount it to read-write. So essentially, we'll talk about rooting later on. But one of the exploits is booting up the system before this line 99 essentially executes. So having a friendly bootloader and having a way to mount the system outside of init would do the trick in this case. Is there reason to ever allow system partition to be writable? There is. Other than OTA. So OTA is the primary reason. It's as a matter of fact, that's how OTA. Yes. Yeah. So OTA is executed basically by the bootloader. And it essentially treats the cache file, and there's basically a one-liner in the file that tells it, hey, you should go into a single user mode, you should execute this script, and at that point the system partition is mounted read-write. Now to do updates of the system installed apps, you do not need to go through OTA, right? So they can actually, there's a mechanism to install the updated applications. For example, system applications like a browser could be downloaded in data app folder, and it can actually overwrite the previously baked in application in system app folder. So that's possible. So in other words, we do not need OTA to just update a browser, for instance. So that's so there's a workaround that. So back to this. That's a little bit about how the file system is organized and what it does. I mentioned in 4.2 data support for multi-user. And when I say multi-user, I mean actually physical users. So basically, you can have 2 people in a household share a tablet. And so again, it's not exactly that we are using Linux UIDs, as in add user Bob. You can't do that. But you can add a higher level user at the Android level that maps to a lower level Linux UID. The way that works is, and as I mentioned, this was introduced in 4.2, but the underpinnings of that were actually already available in Ice Cream Sandwich. The way it works is, first of all, there's a config file in the platform that is going to show that's going to tell the operating system what's the maximum number of users. And typically on devices like phones, that number is set to 1. So although you have a support for multi-user, you're always going to have a single user. On tablets, that number may be as high as 8. So you may have 8 or more users. There's nothing specific that's preventing you to actually compile it with any number you want in there. From the user standpoint, you can just go to settings, user, add, and you can add a new user. Now, what happens internally is that back in the data system partition, which we talked about briefly before. So let me do this. I'm going to cd into just to do that. So cd. So if I go into users, so there's now a subdirectory called users, which is new. And what we have in there is we have a user list. So if I cat user list XML, that's just an XML file that says how many users we have or what their respective IDs are. So on a single user device, you're always going to have one user, and that's the user 0. So if I had more, it would be 1 and so on. Now for each user, there's going to be an XML file and a directory. So if I cat 0.xml, you can see that this just gives you the name of the user. So it says this is the primary user, and this is the one user device. Now if I go into /0, so data system user 0, we now have specific information about the user. So there's basically a SQLite database that talks about the accounts, the package restrictions, things like that. The package restrictions are interesting. Cat. So basically what we have here is where we can disable certain components and certain things on per, or enable per user. So we can grant certain packages and so forth. So multi-user support is implemented that way. So essentially it just maps to, again, Linux UIDs. They're essentially using a mask. So we're still starting, if we have a single user, we're starting at 10,000. If we have multi-user, then we're starting at 100,000. And then we're multiplying that by the UID. So in this case, it would be a UID 0, 1, 2, 3, and so forth. And then on top of that, we're adding the actual app ID. So essentially, by combining these two, UID and the app ID, we're getting a new ID that is basically a combination of the two. So in other words, we have a user per app, per physical user. Yes?
Did this change very recently with Android 42, or is it different from the phone versus tablet? Because on my phone with the vanilla official 42, I don't get that mapping. I get U0A0 is 2000, U0A1 is 2000, so all the apps, it's not an option.
Yeah, so it depends. So it depends on if you have a multi-user device or a single user device. So even though you have 42, for example, this is a 42 device, or it's this one actually is not, but this is a device that's going to have just a single user. So there's going to be, if you go here, you're going to see. Actually, it's hard to do this on a tablet. Yeah, so this is basically just going to be a device with a just default user. In other words, on this device, this number is set to the config maximum users is set to 1. So if you only have one user, then the mask is going to be shorter by 10.
But it's not even increasing by the app number.
It should be increasing by the app number. So do you have, the question is, do you have the apps be app underscore something, or do you have like this format where it's U0?
If you do like ID U0 underscore 847, then 2000.
Okay, so I'll show you where the file is that is governing that. We're going to look at that file, but it's a .h file that's defining when to increase and how to basically start those masks. So we'll take a look at that. Yeah. But on a typical device that has multi-user support, so we're gonna basically have something like that. So U0A3 is gonna look like that UID. What we're gonna then have for each user, we're gonna have a specific user data folder. So each user gets his own copy of basically apps data. So in other words, if you have two people in a house using the same tablet, they're gonna install the same Angry Birds. They can share the Angry Birds app itself, but the data folder for Angry Birds is going to be separate, so their high scores are separate, and so forth. So that's managed by data user partition. So if we do /data/user, ls-al, so in this device, we only have, because we only have a single user, and that user is has a ID 0, that maps to /data/data. So if you had multi-user support, that would actually go to a different /data partitions. So this is going to be remounted as you switch users. So it's going to look to apps the same. So it's going to be /data/data. So if you have apps that are actually referring to the full path, it's still going to work. It's just that it's going to be mounted to a different partition. So that's how that's So essentially, if I had say 11 users, or this would be a 12th user, so we would have /data/user/12, and then we would have, for every single package, we would have a folder in there. So we saw how different UIDs have different how different apps have different users. We talked about that. So that's basically how the data is segmented between users. The actual binaries are not, right? Because there's no real reason to separate the binaries between multiple users because they don't change. So so we're essentially having all the cache and the apps be shared. The native libraries are, as I said, they're now changed. So as opposed to being in the data user ID package, they're basically mapped to data applib package, so to a specific link. So there's basically a link to a shared library. In other words, if I download Angry Birds, and Angry Birds has libangrybirds.so, which is how they do computations or whatever, as opposed to having multiple copies of the same library, the library is now in a new location, /data/applib, and there's a symbolic link for each package, so that the actual lib is now shared between multiple users. So that's a little bit about how that support works, and as I said, it was introduced just recently. So what we're going to talk about next is we're going to talk about permissions. As we said earlier, Android is a permission-based system. So basically, if you have an application, such as an application that contains a service, and you want this application to be able to access, if you want this application to do something that's potentially dangerous, like, for example, access drivers and such, and does this application runs under a system user, we need to protect this application from just having anyone access it. So one way to do that is to essentially say that we require a permission. Now, on the flip side, if somebody wants to use this application, so for example, we have a client activity that wants to directly talk to it, what we would do is we would request that permission. So it needs to match, so it's like yin and yang. So required permission and user's permission need to match. And ultimately, it's the user that gets the little screen and says, yeah or nay, I approve this permission in case of a dangerous permission. There are about 4 to 6 different types of permissions. We'll talk about that. But that's a screen that most of us have experience with. So that's the premise behind that. We can actually see what various applications run as. So, for example, if I wanted to find out various permissions for an application, let's, for example, see we wanted to see the browser. I believe that was the one that we were run as. Let me see, actually, what's the package? Oops, maybe shell. PS, and we had the browser or one of these applications running. Can't do browser, but I can do my application. So Android number. So I can now basically do something as that application. And what I can attempt to do is I can attempt to make a phone call. So I can attempt to run as an underprivileged user, so whatever that UID is, and I can try to basically have this application make a phone call. And in this case, this is not going to work because we don't have the permission to do that. So this application is not granted a specific call permission, so it can't do that. So that's how the kernel in this case is enforcing this. It's essentially failing with the security exception. We mentioned that basically the app level, we specify uses permission and we specify requires permission. So you guys are probably familiar with these statements in the manifest file. Let's take a look at some of the permissions that actually exist in the device. So PM list. Oops. So on this particular device, I can use package manager to actually see all the permissions that exist on this device. So this includes both the built-in permissions. So for example, a permission to call privileged, as well as some custom-made permissions that exist on this device. What we can do with this is we can actually sort them based on various settings. So if I do something like this, I can get a little more details about specific permissions. So you can kind of see that this device has a permission called read status that is enforced by this package, that is a protection level signature, etc., etc. So this is how permission manifests itself inside of the package manager. So now, obviously, there's so many permissions at play, and they're not all equal. So this is from the Google I/O last year, the top 10 list of bad permissions, if you will. So Google doesn't have any curation in terms of what goes into the market, but they do have a curation in terms of what gets bubbled up in the market. So in other words, if you're going to become featured, they actually have a team of pretty smart guys that actually analyze the applications, and they run some kind of heuristics, and they figure if an application is actually possibly a good application or a bad application. So if an application is sending SMS and receiving SMS, unless it's an SMS application, it's a bad application most likely, right? If an application is using system alert windows, it's probably a bad application. There's no real good reason to use that often. If it's an application that's reading your bookmarks and writing to your bookmarks, in other words, tracking what you're browsing, it's probably a bad application. If it's reading, writing your contacts, same thing. Calling a phone number, distinct from dialing a phone number. So calling phone number is actually bad. We'll talk about dialing, which is not bad. Reading your logs is potentially bad because you could be leaking some important information in the logs. Accessing find location. So unless it's some kind of location tracking application, you often can do pretty well with just the course location for games, for example. Get tasks, in other words, figure out what's running. Receive boot completed. So this actually surprised me because it's usually a good place to use for installing alarms and such, but it's number 9 on the list of bad apps to use. And change Wi-Fi state is another one that's bad. I would also add to this list access the phone state. Almost every single game nowadays uses that because they need the telephony manager get phone ID or get device ID to figure out unique ID of the device. And that's kind of like an anti-pattern in figuring out who's using the app. There are better ways to manage that, but a lot of apps depend on that number, which is usually mapped to IMEI number on GSM phones. So this is from Google I/O from last list. So basically, the workaround is that whenever possible, you should not be using permissions that are potentially dangerous, but rather use permissions that are not. So, for example, let's compare the permission to access camera, right? So taking a picture is a potentially dangerous thing. It could be spying, it could be intruding your privacy. DoD certainly would not like you to even go anywhere near the camera. Now, action, so that request is pretty bad, but action image capture, on the other hand, is not necessarily bad because that is just going to open up the system camera application, right? So the user still knows what's going on, the camera is open, and the user gets to say yeah or nay and snap a photo. So that's okay. So this is basically the code that would work around that. So you would start an activity for a result, and you would use image capture request, which would just pop up the camera. You take a picture with the familiar camera application, and once you return from that, you actually on activity result, you get the data back. So that's a preferred way of handling that. Similar thing is true for SMS. So there's no good reason for your application to be possibly secretively send SMS messages out there. This can cost money and intrude some privacy. So as opposed to send SMS, what we can do is we can just create an intent with some data. So in this case, SMS to 415-555-1212 or 1234, and that's going to pop up the standard SMS application, and so users going to be familiar with that. Reading contacts is another example of that. So as opposed to read contacts, just do action get content and access the standard content provider for contacts, for example, or contacts application. So read the phone state. This is the sort of the anti-pattern that I was talking about. So a lot of apps are using get device ID to access the unique the IMEI number of a device. The better way would be to actually generate that number and store it on the device itself, as opposed to have this potentially dangerous permission. Yeah. What would it return? It's really up to whoever built the device to determine what it returns. It just most commonly the default implementation, the reference implementation, is to return IMEI number. Yeah.
So, okay, granted it's not a security issue, it's a privacy issue, and probably it should actually be restricted entirely. But everybody's using that to share data across apps, right? This is how ad networks fundamentally work. So like every app that you make has a global ad network that's going to use it. So it's not really something you can avoid if you're trying to monetize that.
Yeah. So yes, that's correct. Google's been running things very loosely when it comes to security for some time, and this is one of those examples. So, but basically, they're saying now that the best practice is not to ask for that permission. So,
the same ad network can't share behavior between applications, right? And that's a
right? Yeah, yeah,
they want it by
yeah. Ultimately, I get that we need a unique ID per device so that we can identify it as a cookie or whatever equivalent on ad networks and things like that, or for licensing reasons. But the only ID that people kind of figured out to use was the get device ID, and unfortunately, that requires user to approve this potentially dangerous permission, which is read the phone state, which we can actually tell you if the phone is off hook, on hook, ringing, that sort of thing. So it gives the app way more privileges than just access this potentially innocent unique number on a device. So, like I said, it's an anti-pattern. It's been going on in a big way for many years, but it's something that read-only serial number property.
It's what ADB shows back in.
And is that available via like build.os or something like that, or?
It's created. It's initialized at runtime based on
Yeah, it may not be available at Java.
I don't know if the apps can get that.
Yeah. Yeah. To my knowledge, there isn't another obvious unique number on a device that's available to app developers. So basically what they're saying is that, hey, generate your own number and then store it. But this is more work because you now have to worry about storage and all that other stuff, as opposed to just saying, hey, I'm just going to access the number that's there on every single device, and that's why everyone's doing it. So, yeah. Permission enforcement. So basically, there are a number of triggers how the permissions are enforced. Ultimately, kernel has the final say, but native daemons also do the same thing. Application framework has a way to do that, and application components can enforce permissions as well. So as we basically discussed already, init process sets up the ownership. It works via init.rc file, which I showed you briefly. There's another file that's of interest, and that's ueventd.rc. And so cat uevent rc. So basically, this file sets the permissions on various device drivers, right? So we're setting up who can access what on this particular device. So for example, to install alarms, somebody needs to be either a system or a radio user. Or to access camera, it needs to be either a root user or a camera user. So this is now handled by ueventd at boot time. And it's one of the very first daemons that is started by the init process. System.rom also has a file, and I mentioned this file earlier, and this is the file that actually creates all the masks for users. So unlike traditional Linux that has etc password file, which we don't have on Android, there's a file that looks like this. Just 1 second. So it looks like this, and this is where we're setting up those masks. So these are the various AIDs now that they're going to map to various UIDs, right? So basically we're saying that the root is 0, system apps start at 1000, and they keep on going. So we then have the 2000, 3000, and then we're starting the actual app users at 10,000 or 100,000 on a multi-user devices. So that's the first app user, and typically this is going to be your launcher, is going to be at 10,000 UID. We're now mapping the users to these UIDs. So if we have a root user, we're going to map it to UID 0, and so on. And then we basically have file system permissions that we're also mapping, so we're setting the permissions. So for example, the fact that the data permission is isolated from anyone else, in other words, the cornerstone of the sandboxing on Android, that's managed by basically this file setting up that it's a system for user and for group, right? And we're giving it 771 mask for data. So we're starting generic first, and then more and more specific. So that's that's why when ultimately we go on a device and we ls-l/data/data, we can see that this is now, well, actually if I ls/data, we can now see that, let me kind of clean this up, that the data partition is owned by system, and has that mask of 771. So that's where that is configured. So we're now doing that on a file basis. So this is doing it on a directory basis. This is now doing it on a file basis. So it gets even more specific. So we're now setting permissions for each specific file, and then ultimately we're doing it on per user basis. So it's figuring out the permissions on for a specific user. So this is the replacement essentially for what we know in standard Linux as a etc password file. So that's kind of how the users are dynamically essentially allocated on Android. So that's the Linux enforcement. Now, what's interesting is you guys are familiar from the app level that we have users, right? That we have permissions. So we've all seen a permission, for example, Android permission internet. So how does this really work? So let's take a look at this file. So if I open that file up, essentially, this is the file that's listing every single permission that ships with Android. So this is the operating system level Android permissions. And there's our internet permission, for instance. Essentially, what happens is this permission just gets mapped from this high-level Android construct, android.permission.internet, to a Linux kernel or Linux GID inet, right? So now we're basically just mapping. So essentially, when install D downloads, say, Angry Birds, right? It analyzes its manifest file. It sees uses permission line, right? And that uses permission line says Angry Birds wants to use permission for internet, right? So what then happens is if the user says yeah to that permission, that app gets assigned a GID of INET. Okay. So from this point on, it's really just up to the kernel to manage the permissions, right? So now we have our app that we downloaded granted permissions for internet, and that's how it works for pretty much all the other permissions. What follows that is basically the enforcement, which we're going to see in a little bit, but that's now enforced at IP level. Who can open a socket is basically controlled by kernel to basically say, hey, is this process member of that group? So we'll see that later on. So we talked about this file. That's what we did. So that was the file that we looked at how we manage the UIDs for apps. And this is what we were just talking about. This is so-called paranoid network security. And I'm using internet just as an example of how most of the other permissions work. So how we map them from this high-level Android constructs to the low-level Linux constructs. So as we mentioned, so this is the manifest file. That manifest file uses permission. So that permission gets mapped in this operating system level file to INET group. This INET group is in that replacement for a etc passwords file mapped to the actual INET user, or more specifically mapped to the UID of 3003, for instance. And now what we basically have at the networking level, the kernel level, is we basically have a little check that says, does it have access to network? And we basically check, hey, is this part of that group? So that's kind of how we have an app ultimately be able to do something or not be able to do something. So this is at the kernel level, yeah. So basically the confused deputy has to do with not that app actually executing that request directly, but confusing another application that has those rights to do that. And so we're now talking at a very low level kernel enforcement. Above the kernel level, we basically have the apps. We have the frameworks worrying about permissions, and then we finally have the applications. So if an application gets an intent to do something, is it really validating that intent? Is it a valid intent, and so on? So now that's going to be at a higher level. So we'll get into some of those concerns. So this is just the mapping of the high level permission to a low level Linux GID. So this is how it's enforced for IPv6 and v4. So this is some other kernel changes. It's not really that important for this. So now that you have this permission, you can also you can create your own permission, right? So when you create your own permission, you can blanket protect an application using that permission. So what we can do is we can protect all the components with static permissions. So activity we can protect against being started. Service we can protect against being started, stopped, or bound to, right? Provider we can protect against having data be read or written. So it's the only one that actually has two different permissions. And the receiver we can basically protect who is allowed to send broadcast to this receiver. So those are basically our ways to protect some of these components. So let me give you an example of this. So let me show you. Actually, let me show you like this. So I have an application here, and so I have a service. And this service currently doesn't require any permissions, right? And that's why we have lots of warnings. The newer tools are actually warning you against doing things that are potentially not so good from security standpoint, but they're still not making it illegal. So basically, this service is not protected in any way, shape, or form. So I'm looking at this piece of code. So essentially, anyone can access this service. And I have a client that I'm going to run, and I'm going to have this client basically access the service. So this client is just a little Fibonacci application. So if, for example, if I say I want to calculate the Fibonacci of 23, what this is going to do is it's going to go from one process. So these are separate processes, right? Very important. So one process, one application is going to contact the other application via the binder IPC, and it's actually going to bind it and calculate the result. So the Fibonacci of 23, we get the data, and that's basically what it is. So now what I can do is I can define a permission, and I can statically protect this application. So let me zoom in so you guys can actually see. Now, there's only basically two things that you must provide for a permission. One is the name. And the name can be anything, so you can just make it up, permission access, right? So I just made up a name for this permission. And what I should also provide is the protection level. And protection level is going to be one of these couple of different protection levels. Normal is a normal protection. It usually doesn't even ask the user if you're going to grant it or not. It's more like, hey, there's a permission there that you should use. Dangerous is the permission that you actually get asked as a user to OK at install time, right? We're not going to see this with debug key signed apps because it just doesn't they don't kind of want to create a friction in the development time. But when you download Angry Birds and it uses internet permission, you're going to get prompted with this. Signature is essentially going to be automatically granted to the apps that are signed with the same key. So this is where basically it becomes interesting how you can create a federation of your own applications. So you sign them with the same key, and you can enforce signature-based permission, and that's the only way they can get access. Signature system is going to be granted to those that are signed with the same key, as well as those that are baked into the platform. So essentially, remember how I said they're the same apps, but there's something that the apps located in system app folder can do more than standard apps, and this is it, right? So in other words, they're slightly more trusted because somebody actually went out of the way to download these apps and pre-install them on the platform. And this is very useful in cases where you're building a ROM and you want to include third-party apps, but you don't have the source and nor you can re-sign them. System is just the system, and development is development. So I'm just going to go with a signature level application in this case. So if I now define a permission, what I can do next is I can enforce it. So if I want to blanket protect this service, what I can do is basically I can say this service requires that permission. So basically now nobody can access this service except those that have the permission to do so. So if I reinstall this app, so that install D picks this up and updates that /data/system/permissions file that we've seen earlier. And if I rerun my client, and I try to, I need to bind it. So let me just do something really quick. I'm going to touch my client so that I cause the rebuild, and then I'm going to run it so it gets reinstalled. And it just died, right? So it just crashed. So, and now if you actually were going to look at logcat, you would see that we got a security exception thrown somewhere here. So not allowed to bind to the service, right? So we basically blanket protected that service. Now if you wanted to grant access to our application but nobody else, we would basically take the same application, permission. So this is the permission that we're enforcing, right? And if you go here, then the client can now say that it uses permission with the name that. So now the client says that, then in case of a dangerous, it's going to prompt the user. In case of a signature, the system is just going to compare the signatures. The part of the system that's going to do that is basically the activity manager when it's starting it. So it's going to basically say, hey, is this guy allowed to start? And so if I restart, put some number, use calculate Fibonacci, the client service works again, right? So that's working in this case. So that was the static permission enforcement. So that's basically what we talked about. You can kind of read on your own. What we can also do is we can dynamically enforce permissions. And this is what the operating system does all the time. So in other words, operating system doesn't say, hey, you just don't have access to a location service at all, right? That would be kind of tough for them to even implement. On the system level, everyone's got access to every single system service, but then the system service itself is going to enforce the permissions. So in other words, it's doing that dynamically. So for example, everyone can bind to a location service. It's actually pre-bound, but that's beside the point. But depending on what kind of a location you want, we can dynamically determine if you have rights to access GPS versus mobile network, right? So that's done dynamically. So essentially, again, our client, our service, right? Let's say it's a location service or food service, it doesn't really matter. Let's say I have some native piece of code, like .so file, native library. So if my activity wants to go native, it can. Everything's fine with that. But just the fact that we have C++ code in our app, and this is underprivileged app, right? So not some A47, right? It doesn't mean that this app can now have access to some driver, right? The kernel is going to block that. The kernel is going to block that because uevent-d sets the permissions on /dev, right? So basically, your lib is not going to have access to that, right? So that's not how the system works. The way the system usually works, or most of the system services, is system services are running under the system user, right? Or some kind of privileged user. So this privileged user is going to have access to that driver that you want. Let's say GPS, for instance, right? So there is going to be a lib GPS, for instance. There's going to be a wrapper, some location something.cpp file. There's going to be a Java file that's going to provide access to that JNI file. And then we're going to have a location manager, which is misnamed for location service. So we're going to basically have location service here. Now what's going to happen is when you want to access it, the location manager here, it's going to ask via the binder, it's going to basically want to access that, and the permissions are going to be checked at the context level. So the context is basically going to enforce the permissions dynamically. So the context is the one that owns the binding between the client and the server, and it can actually enforce that. I'll kind of let me just kind of give you a quick example. So in my client server example, if I created another permission, I'm going to copy paste this one. I'll create a permission to access. I'll call it access native. So for example, I'm going to do a dynamic permission check depending on which algorithm you want to use, right? So now inside of my service, so let me just find my service implementation. So I'm not using, unlike before where I blanket protected the entire service, I'm not going to do that. I'm going to be dynamically checking this permission. So what I'm going to do is inside of my Java file, and it's usually done at the Java level, I am going to, when I handle, for example, native method, so this is a call to a native call. I think I have a couple of calls here, but let me just protect, for example, native iterative. So what I can do is I can check. In this case, do we actually have the context? In this case, we actually don't have the context. Should have passed the context in. Let me do this. So as opposed to typing all that, just in the interest of time, let me switch to, actually I don't have the branch. So basically what I would do if I had context, let me just find it, although I don't have it. Private context. What I would do is I would check with context, check calling or self permission. So basically I would enforce a permission here, right? And we'll basically check, is the caller allowed to even call this permission? And I would basically compare that to a package manager dot organize imports. Zoom in so you guys can see. Permission granted, for example. So unless we have a permission granted, right, I'm not going to let this go further. So what I would typically do is throw new security exception. Right, something like that. So now the only thing that's missing in this guy is basically a public constructor to actually pass in the context, because I don't context. And there's that context. Here's context. So so basically, if we now create this with a passing of this in here, we're now dynamically enforcing this permission. So yeah, so now if I try to run, if I install this service, and I'm gonna rerun my client very briefly, and if I run my Java algorithm, I get the result. But if I run my native algorithm, it dies, right? And if you look at the logcat, you will basically see that we threw a, this is not my permit, this is somebody else's, but we would see that we have a go away security permission in there. So that was dynamically enforced, right? So this is, I'm not just making this up, hey, this is interesting and you know, cool, but this is actually how the system does it all the time. So if you look at, for example, the vibrator service, right? So they're gonna do exactly the same thing. They're gonna basically say, if you wanna vibrate this phone, we're gonna first check dynamically that via the context that you actually have the vibrate permission, right? So this is a simple example. And if you don't, it's just gonna throw a security exception. So that's one example. Location, it's one that most people are familiar with, does exactly the same thing. So there's going to be a private method called check permissions that's called by pretty much every single API. And what it does is basically says, you know, does the caller have GPS? If the provider is GPS, does the caller have the permission to contact that? And if not, it's going to throw a specific security exception for example, location manager. So that's what we just talked about, custom permissions and what the levels are. You can kind of read that on your own. Adding custom permission. This is that example that we just walked through. So basically, we have our service that was enforcing some kind of permission, both statically and dynamically, right? And it actually had a native code that was, in this case, calculating Fibonacci, but it could have been accessing a driver that typically would be off limits to any other application. So that's the design of that, and this is all spelled out in detail, so you guys can kind of go through that. I know I went through it a little fast, just in terms of because of the time. Content providers also have permissions. What's different about content providers is that there are two permissions. They're based on read and write. So basically, you can grant a read permission or you can grant a write permission. So that's the significance of that. Public versus private components. So traditionally in Android, when you define a component, by default it's exported, which means that this component is now available to everyone. And for the longest time, that was not a problem, right? So basically, if I had this service here, and unless I had the permission, so if I take this permission out, that was not a problem before, but what you're seeing now is the tiny little warning. They started to actually give you a warning that basically says exported service does not require permissions. So now they're saying, hey, you know, this is something that's potentially dangerous. You're basically leaking to the entire system your intent filter. In other words, every single component on the device, if it knows the intent filter, which is, you know, readily available in a readable manifest file, can start or stop or bind to this service or launch an activity that's not meant to be launched from outside and so on. So that's a security concern. So luckily Eclipse now started giving you at least the warning, but the solution to that is to basically just say exported false for the components that you do not want to expose publicly, which should be the most components unless you're specifically exposing them publicly. So this should actually be, the default would make sense to be the reverse, but just because the way they architected it, we're carrying the baggage of that with us. So that's a little bit about exported components. Intent broadcasts. Broadcasts are slightly different. So basically, if you send a broadcast, it goes to everyone unless you specify the permission. So sometimes people do, sometimes people don't. But you can basically enforce who is allowed to get that broadcast. In other words, which receiver can be on the receiving side. So if you specify that, then the receiver actually must own the permission to get that broadcast. And if it doesn't, it's actually not even going to know that it doesn't have a permission. In other words, you don't, as a receiver, you don't get, nobody knocks at your door and says, "Hey, there's something for you. Can't tell you what it is." You just don't know what you don't need to know, right? So that's kind of how the receivers are slightly different. Unlike an activity, if you try to do something you're not allowed to do, like connect to internet, it's just going to blow up in your face and it's going to say, "Hey, you don't have a security permit. You don't have the internet permission. Or did you forget to specify?" So it's more of it's more informative in that case. But given the nature of receivers, any information would be too much information. So that's why they don't do it, which makes sense. Pending intents are interesting. For those of you who haven't used the pending intent, is basically an intent plus the action on that intent that's kind of wrapped up and meant for somebody else to activate it at some future point in time. So the ownership or the identity of that pending intent is owned by whoever created it. So that's an interesting thing, and that's usually the way you want it. Although the one that's actually activating the intent or pending intent or triggering it can also fill in some information on that as well. So that's a little bit about the application level security. That's kind of interesting new stuff in Android. What I want to go through is data security. Basically, Android provides encryption, the different levels of encryption at different parts of the stack. So data encryption exists as part of the OpenSSL, as in the native library. So it's in lib, system libSSL. What basically it provides in conjunction with the Java bouncy castle, which is basically the Java implementation of the Java cryptography extension. It provides public-private key encryption. So you can basically use it to open up do the key management and so on. So this is an example of how to do HTTPS connection or SSL connection. This is how you would read from HTTP. So that's provided on the platform. We have an example that just shows how to use cryptography library itself. So all these examples, by the way, are available at github.com/Maracana. So they're about a couple of hundred, or about 100 little open source examples. So this one is called Secure Node. What it basically does is it uses the crypto library, the bouncy castle, and it uses it to encrypt the message. So I could basically create a message. I could say this is secret, right? I can save this message. What it's gonna do? It's gonna ask me to generate basically the key, the seed, not the key itself, but the seed for the key. So I'll say secret, right? So if I do OK, we're going to use this password to generate a key, and we're going to use that key to actually encrypt this message and store it. So now if I close this application, actually do a total close, and then if I try to reread this data from Secure Node, it's going to ask me for that password. If I mistype it, the message stays secret. If I try again, can I actually try again? I guess I need to restart it. And if I actually type secret, it's going to decrypt it. So that's the message that we stored. So the code for that is, let me just close all this. So that's using the bouncy castle and JCE to do that. So we basically have a little crypt utility to generate keys. That's creating the secure random object. Is basically getting the seed. The seed is based on the secret, and then we're using that as the key. And then later on to encrypt and decrypt, we're using the cipher that was generated based on that key and based on that seed. So that now becomes how we encrypt and decrypt the message. So the entire, this is the crypto part of that application. Everything else is the UI, so it's not as significant from security standpoint. So this is the encrypt using that cipher. So we basically need the cipher and we encrypt it, and we do the opposite in decrypt. Right? So that's using the built-in libraries that are part of the Android. So that's the code for that. There's a whole disk encryption. So this is now at the operating system level. That was introduced in 3.0. It's been improved since, but basically what it does is provides for the encryption of the entire file system, encrypts your data partition, your SD card. It's slow. We've done some analysis on this. So what we've done is we did writing of 1 gigabyte of data, just to kind of time it, and it took about 100 seconds, 103 seconds to be precise. And then what we did is we did a reading of 1 gigabyte of data, and it took about 46 seconds. So 145 roughly, right? After encryption, so we repeated the same thing. So the reading took 107 seconds. So it's not that, the writing. So it's not that much. You're looking at 3% degradation in speed, right? But reading the encrypted data took 70 seconds. In other words, it was about half as slow in terms of performance. So there's a little bit of a hit. Sure, you can turn on the encryption of the entire file system. You're gonna pay the penalty in performance, and that's basically what it is. This was done, some time ago on Galaxy Nexus that we performed this. They've been improving this since. So let me see. In 4.1 and 2, they actually changed it a little bit, so the performance got improved. But I actually don't have the exact data what the numbers are on that. VPN, there has been a change to VPN. You may recall that for a while VPN was based on Raccoon framework and was basically entrenched into the operating system. There was even quotes from Andy Rubin that they're never going to expose it because it represents a major kind of surgery to the operating system and security issue. But this was something that was kind of blocking Android from becoming a serious enterprise device because there was no VPN support for any meaningful VPN protocols. So in ICS, they basically provided a way for apps to essentially hot swap VPN so that you could download Cisco VPN, for example, and install it. So the way that works is now there's a system warning. So when you actually want to do something that's potentially dangerous, it pops up a message that says, hey, are you sure you want to do this? It's going to allow this app to basically control the entire access to network communication. So that's about VPN. Key store, keychain APIs, they've been built into Android since 1.6. It got facelift in 4.0, but basically it's your management of system-wide management of key stores. It's used for storing everything from your certificates and things like that. So that's part of the operating system. Application encryption, we talked about that briefly. Routing, I know this is a topic that a lot of you are often interested in. We mentioned this earlier, typical Android device is not rooted. You probably don't want it to be, or you probably don't want users to have a rooted device to begin with. So basically, the key to essentially unrooting or getting access to root on a system would be to remount your system partition. So it could be something as simple as, mount like this and basically specify read-write rights. Of course, this would fail unless you have root to begin with, so it's a catch-22. But if you were able to do that, you could then basically create an SU command, chmod it, and give it rights, and then you could repackage your file system to be read-only again. But again, the catch is you can't remount this partition once it's init mounted to begin with. And the reason for that is, again, because it's booted that way. So if you were able to do remount, that would have to be done before the init runs. So in other words, before the kernel starts. So most of these rooting procedures are done at the bootloader level. So basically before the kernel even got booted. Now, if you have a rooted device, the problem is that now everyone has access to root. And that's why you don't usually want that, because any random app can just do whatever it wants, right? So one sort of workaround that is to use the super user app. So there's an app that's kind of going to provide meta provisioning of what you can or cannot do. Is just an app you download from the market. So in other words, you have root, but now every time somebody tries to do SU, it goes through that app, and the app warns you as the user and says, hey, do you grant sudo to such and such application? So that's kind of one workaround that, but again, you would have to kind of worry about that. These are some other exploits that we know about. So udev exploit, so that's been patched. ADB, setuid. Exhaust attack. Basically, ADB wasn't checking for setuid, so after a while you could actually change the UID on it. This is a zygote attempt, basically exploit also to do with a setuid. Ashman protect attacks. So these are all known attacks. This is from 4.3 from Gingerbread. Buffer overruns for Vol D, so that's another exploit. So I'm just going to kind of list them up. So this is just the Linux local privilege escalation attack that was provided. Drivers. This is specific to Samsung. So Samsung basically had a driver that the physical memory manager that was set to be readable and writable by all. So that was basically an exploit that was specific to Samsung, and was used by their camera and their Gralloc hulls. So that's a little bit about that exploit. WebKit, again, it's an exploit of this specific library. It's not just specific to Android. It actually also had to do with iOS. And again, it's based on buffer overruns. It doesn't give you a root, but what it does, it allows you to basically have your browser execute an application. So it's sandboxed within that application, but still it's a pre-installed app, and was patched in 2.2. So the point about rooting is that Android is designed in such a way that you don't really know who the apps really come from. The signature system only guarantees that the owner of the signature can only update the apps, but it doesn't really tell you who the owner really is. So there's no certified authority or anything like that. So once you have a rooted device, you basically have the problem of managing all these untrusted apps that come from third parties that we don't really know much about. So that's something to worry about. So those exploits then become really hard to track and attack. One of the systems we mentioned is the super user app, but that's just it doesn't really do all the justice. And there are also many malware rootkits that are available there. So OEMs carriers are usually, not all of them, but they're usually slow about providing the updates and patching those exploits. So that's basically a little bit about the known exploits of the of the root. So that's something to think about before providing a routing device. A little bit about device administration. This is an interesting API that was provided by Google a couple of years ago, and it's a little bit went quiet. Not a lot of people know about it, but basically the premise behind this is that Google essentially said, look, in corporate America today, most people have two phones, right? You have your personal Android phone or iOS, and then you have usually some company-issued BlackBerry. It used to be BlackBerry, but some kind of corporate device. And you need to use one for work, the other one for personal stuff. So they basically said, look, we see the future as you have a single device. And it's your home device, it's your personal device. And you're going to use this device to download, Angry Birds and some malware and spyware and apps like that. And they're going to go to work and you're going to access your private corporate secure network with the same device. And they say there's a way to do that. So what they've done is they basically provided the plumbing, the framework to administer devices, to manage a fleet of devices, right? Just to kind of give you an example, we run entire business on Google apps, and so basically what I can do, I have a couple of my devices here. What I can do is I can basically I can locate my device. I can, if it's on a network, I can even, if I'm on a network, I can try to locate it. Of course, I have GPS issues here. I can ring the device, but right now my device is probably on a silent mode, so I'm not sure if it's actually going to make any sound, but we'll find out when it actually gets located. So it's still trying to locate the device. Sorry, I'm locating the wrong device. Oops. So yeah. So basically it just starts. But the point is I can remotely find my device, I can remotely reset my device, etc. So that's kind of the gist of this framework. It basically consists of a couple of things, and we actually wrote an example how to write an administration to a device. But essentially, you're creating an app that's essentially a super app, right? This app not only has permissions, but it can actually enforce policies. Now, policies are way beyond, quite different than permissions. They allow an app to do things like wipe out the entire device, right? Disable camera, lock the screen. In the next version, they're going to actually self-destruct it, so I heard. So there are lots of kind of like, things that you can do. Well, actually, not that many. It's about half a dozen things, right? So we're going to kind of take a look at that. So basically, what you can do via policies is you can set maximum inactivity, minimum number of password attempts, maximum number of failed password attempts, how long the password is, when does it expire, and some history restrictions, and so on. They added a policy for a camera in ICS. That was probably a request of DoD, and that's about it. So what your app does is these are kind of the moving parts of the app. I'm not gonna go through that because we don't have time. But essentially, you're defining a receiver. I can actually run this app, and again, it's available in our GitHub tree. So let me kind of run it. So what this app is going to do is going to say, hey, I would like to become an administrator of your device. So this is where you're basically about to give the app super rights, right? And this is essentially what you would trade as your privacy if you want to take your personal device to, say, your company network and want to connect it. So the administrator would usually say, you got to activate it. So in this case, I'm saying, all right, let me see what this is all about. And this is now a system pop-up. So this is now a system pop-up similar to the one where you're granting permissions to the application, but you're granting policies. So this app wants to be able to erase all the data on my device, wants to be able to lock my screen, to change my password rules, to monitor unlocks, and et cetera, et cetera. So it's pretty significant sort of set of things that it's asking me. If I say activate, now this app is administering my device. So if certain things happen, like I attempt too many times to to log in and it fails, this app is going to have a broadcast receiver that actually gets notified about that. And now you can do some certain things. You can ping the mothership and say, hey, this device is lost. Or you can actually reset the device, or you can log the device. So resetting the device is actually going to factory reset. So it's going to nuke all the user data on the device. So this is kind of like a Google attempt to provide security at the enterprise level to corporate America to make them feel warm and fuzzy about actually bringing Android into the workplace as a single device. Now, Google is just providing the plumbing for this, right? So this is just an API that's pretty well thought out, I think. But there aren't many apps so Google has their own Google Apps app, right, for business users of Google. But other than that, third parties are basically coming up with solutions to solve that security hole. So that's a little bit about how that app works and how to implement it. So I'm going to skip to that. So those are the details. And again, all the code is in the source tree, in the Git tree. Malware. So how do you protect now your device from possible malware, right? So basically, we need to first identify it, right? So figure out what malware is. So there's some studies that are done, looking up at some of the characterization and evolution of malware. So this particular study looked at 1,200 different malware samples, and they found out some signatures or patterns in malware. They basically concluded that 86 of them are repackaged versions of existing apps with some malicious payload. So basically, they would take a popular game or a Bank of America app or something like that, and they would basically add certain hidden features, and sometimes those features could be hidden in what looks like a pack or a Java package or class that may look legitimate when you look at it with just a naked eye. So that's basically majority of the apps. Some of them don't do that, but so a small percentage, about seven of them. But basically, they just ask to get updated with the version of themselves. So they basically go and download a version or additional payload as part of the app and add it to the application. So basically what they're adding is either an asset or a resource or something of that nature. It's sort of similar when you have a game that goes and downloads the next level sort of thing, right? Sometimes they're using even the Dalvik class loader. So basically, you can have Dalvik dynamically load the library. So you can say, hey, I'm going to download the payload as my next level in a game, but then have Dalvik try to load that payload. So these are some other things that they discovered. So drive-by downloads, applications that are basically analyzing the user device and figuring out what's installed. We have about 13.8% of applications have malicious behavior. Out of these, 83 use boot complete or SMS receive. So remember the top 10 list of bad permissions that Google has. So it kind of maps nicely to this 83%. So these are some of the permissions that these guys found. So internet is in 98% versus 89% in standard apps. So you can kind of see the differences. And based on this, you could build some heuristics and say, hey, this app is potentially a malware, right? So these are some other numbers in terms of what they come up with and so on. So how do you detect it? Well, there is a package manager. Package manager is exposed via API. So package manager is at the Java level. At the low level, we basically have the install D. So the code for this application is actually in anti-malware. So you can actually see this app that's going to analyze all the other apps once I install it. So it can actually scan my packages, look for signatures, and find a specific app. And it says this app looks like potential, malware. You can proceed. Now this app can actually uninstall this app. So yeah, basically wrote a little app that's uninstalling my own app, anti-malware. So it's basically uninstalling this app. So that's how virus protection programs work. This is basically the blueprint for virus protection in the following slides. So I'm going to skip through that, how to remove it. There's SC Linux, which is a project and NSA to SC Android to do something similar to SC Linux. So that's basically a security enhanced Linux. And these are some other concerns. The biggest one that I would mention is the social engineering vectors of attack, basically fooling the users into doing stuff that they're not supposed to be doing. So that's basically what I had. So there's give me a stop notice. So essentially, we talked about stack a little bit. We talked about essential security issues, so architecture, UIDs, file access, multi-user permissions, app signing. We touched on some of the advanced security issues, like encryption, routing, device admin, malware, and so on. So, of course, security is a really big topic, means many things to many people, but I kind of tried to touch on many, many different things. Hopefully you guys found it useful. If you have any questions, comments, concerns, that's my contact info. Feel free to hit me up. And these slides are available online. Again, that's the shortener there. And the video of this presentation is going to be available online as well. So any questions? Well, thank you guys. Appreciate it.